Great to see everybody here today. I'm Patrick Taylor, co-chair of the PISMIT panel, Process Studies and Model Improvement, along with Sophie Clayton. We have a special guest that will be introducing the speakers today, but I want to give you a quick overview of why we're kind of here today and what the goal, the role of the panel is. So US CLIVAR is here to foster the understanding and prediction of climate variability and change on pretty much all time scales, intraseasonal to centennial timescales, really with a focus on how the ocean interacts with all the other components of the climate system. The role of CLIVAR is to serve the climate science, climate community and society and coordinate and advance research. The panel, US CLIVAR has three panels. This is the Process Study and Model Improvement panel. Our mission is to reduce uncertainties in general circulation models. And we do this through a number of different ways. One of the ways that we try to facilitate this is through this webinar series where we're trying to follow various different process studies and try to understand how we can better use that data to accomplish this mission, which is ultimately physical understanding and reducing uncertainties in general circulation models. So what we do as a panel is review, prioritize, and coordinate, looking at these different process studies and different activities that we can undertake to help facilitate and advance, move us forward towards accomplishing that goal. We develop and encourage mechanisms, which include community workshops, working groups, etc. We advise US CLIVAR and help facilitate and foster and coordinate joint agency participation. And then we also liaise with the other US CLIVAR panels and work groups as well. So with that, that is kind of the reminder of what we're here to do. And so I'd like to turn it over to Charlotte, our co-chair of the panel for the last 2 years, to introduce our speakers today. Thanks.
All right, thanks, Patrick. So today we will be hearing about the convective processes experiment, aerosols and winds. We're honored to have two distinguished guests, Professor Shuyi Chen and Ed Zipser. First, to introduce Shuyi. Shuyi is a professor in the Department of Atmospheric Sciences at the University of Washington. Following earning her PhD from Penn State in 1990, she began a postdoctoral position with Bob Howes at the University of Washington, where she was quickly put to work in the Western Pacific as part of the Toga Core Field Campaign. This is when I first met Shuyi. Following that, she, doing some additional work at UW, she then served as a professor at the University of Miami from 1997 to 2017 before returning to the University of Washington. One reason I'm super excited to have Shuyi here is that I find her unusual in our field in that she is both a leader in designing and collecting observations of convection, but she's also a leader in using modeling studies to better understand ocean atmosphere coupled processes. Her research focuses on advancing understanding of the role of air-sea interaction and the dynamics and predictability of tropical convective systems, wind-wave current interactions in the upper ocean, and in refining the representation of these processes in models. Ed Zipser, who I think will be joining us momentarily, almost needs no introduction. Ed earned his PhD from Florida State University in 1965. I think Ed may be the one person in our field with the most process study experience that I can think of. In looking at his CV, he has participated in no fewer than 3 and up to 7 field campaigns per decade since the 1960s. It's just astonishing. Ed specializes in understanding regional and global distribution of storms, heavy precipitation, and the ability of satellite observations to accurately measure these events. Throughout his career, Ed has served on many editorial committees, numerous NASA panels, and as well as Shuyi has received many honors and awards. I may have forgotten to say Ed is a professor at the University of Utah. And so we're super honored to have Shuyi and Ed talk to us today about CPEX-AW. So I will turn it over to you, Shuyi.
Thank you so much, Charlotte, for that great introduction. Yes, we met first time during Toga Core 3 decades ago. Yeah, so since then, there's a lot more fuel campaigns. That was my first one. And I think the one today I'm going to talk to you is about my 10th one, and add probably the 39th major fuel campaigns. This is somewhat informal. I have to say that I may not go through all the material, but I probably have a little bit more than I really needed. So just let us know when time's up. So this particular fuel campaign, it's called a convective process experiment, aerosols and winds. We have several major or very diverse science objectives. So I'll get to these when we go through the actual fuel campaign part, but I'll just put this up front to let you know we're first trying to understand the interaction of a convective cloud system and the tropospheric winds. As a part of this, Aeolus, as you know, first active sensing wind satellite was motivated by prediction in the global prediction by ECMWF. Tropical winds is probably the most important driving force for many things, especially the global circulation. So they've been putting over almost 2.5 decades effort to get this in space. So this particular program, as you see, is jointly with the ESA with a larger effort. So our team also geared to observing the vertical structure and the variability of marine boundary layer. That's another big thing for climate modelers. You probably know we're having the ITZC, double ITZC problem in models forever. And this part of this effort is actually trying to observe in wind and convective structure at the same time. So we're also investigating how Africa easterly waves and dry air intrusion in this region, the Atlantic basin. So then we also investigating the interaction of winds, aerosol, clouds, and precipitation in this basin. And that's the picture is our team in St. Croix. So the large science objective was this joint Aeolus Tropical Atlantic campaign of JETEC has quite a bit of a common interest from several different countries. So we're interested in the easterly wave and jet structures and ITZC itself and tweet winds and so on, so on. Not only regional, they all have a global implication for these physical process as we're really focused on process study itself. So the campaign has 4 aircrafts. We have NASA DC8, obviously, and then we have German Falcon and French Falcon and a small aircraft from the Slovenia. Then we also have Greek agencies have a land-based observation in Cape Verde. So this was our original plan for this large field campaign taking place in 2020. So you all know that we didn't go there due to in the middle of COVID. So things got delayed, and luckily satellite lasted a little longer than we thought. So we end up did go through that a little bit. So just for your benefit of thinking what's unique about CPEX-AW, because obviously we're addressing quite a lot of a thermodynamic and the aerosol and the clouds and a really comprehensive way of measuring things using the largest aircraft in the world, DC8. This is the one that we did write a report on, that National Academy report on. In this particular setup, we have a full board of remote sensing instruments. We have the DAWN, which is the scanning wind LiDAR. This is a very unique instrument that actually is a LiDAR, but scanning that can provide us the wind using Doppler effect. And then we have the APR, is an airborne precipitation radar with a 3 frequency band, Ka, Ku, and W. Then we also have a microphysical and the drop sounds. Another really cool instrument is this high altitude LiDAR it's called Halo, and observe quite well in high resolution in terms of dust and the dust concentration, humidity, and so on, so on. We also have a microwave radiometer based Hamster drop zones. I guess I already mentioned that. So anyway, this field campaign is unique in the way we are right in the middle of pandemic. Many field campaigns I know had that as well last year. So what we end up doing is we end up have probably the most prepared and most best prepared field campaign ever, because we did so many dry runs in the virtual space. So we sampled our field in real time during the season. We were supposed to go in the field 2020, but we did it virtual. So this is our team, actually several pages of this. So I'm just going to sort of mention that how we did this. We pretty much did this every day. We do flight planning, and we use daily forecasts led by our graduate students team. This eventually translated everything into the real-time field campaign. Then we do flight strategy in virtual space. I'll talk you through about that. And also we will have a verification team and so on, so on. Pretty much like a real thing. And this is organized with the ESA teams too. It's a kind of a challenge to get all time zone worked out in the virtual space. And we're largely using this model as virtual space for our flying. So we're basically flying aircraft in the model fields. This model is called a Unified Waves Interface model, developed by my group over the years. It's a coupled model, has the WRF and multi-nested and different resolution. We usually run to the highest resolutions clouds resolving at 1.3 kilometers. We also have a wave interface that actually is very relevant to study air-sea interaction, and HICOM, that ocean circulation model. As you know, this particular region, this ITZC setup is extremely important for convection. As you will see, the South Pacific Atlantic cold tongue pushing through, and you also have dust on the other side. So the ITZC is extremely interestingly situated. And then the model forecast every day being used for our dry run. Like the ITZC, you can see the convergence. And even though the large scale convergence is called for ITZC, but the convection is very specific and in the high resolution model where they actually form. So that was part of our science objective. So during the dry run, we went through all the possible scenario. We do Aeolus underflight because the satellite was flying, and these patterns are set up to follow Aeolus. We will do the ITZC and the dryer intrusion, and then we sample the ITZC. This is all during the time we did a dry run. We fly aircraft in the models. And then we have a joint aircraft. Then we follow tropical cyclone formation and how we sample ITZC, and then follow that through the life cycle and so on, so on. So this is one example of how we did a 3 aircraft sampling in virtual space again. So different tracks represent different aircraft. DC8 has the longest range that will fly through the system, sample repeatedly, both north and south of ITZC. We want to get the convergence and also boundary layer sampled as much as we can. And then the French Falcon has the most sophisticated aircraft with microphysics and a lot of other things, and German Falcon has wind lidars as well. So without much of the details, we did, like you can see, these fields are sampling the models. So we're trying to figure out what we actually see or what we can see. This example of we are looking at the DC8 instruments, winds, what we were sampling through these winds, we realized there's a huge amount of a middle level jet and some very complicated boundary layer structures. And this is mimic what Hilo will see. And and so on, and also APR3's reflectivity, and all in the virtual space. So at the end of the virtual experiments, we did 3 period time, both in 2020 and 2021, right before we went into the field. And this is what we left ourselves to say, you know, we can sample really complicated ITZC region, the inflow from north and from south and satellite. And this is what aircraft did using our coupled model to do that. But we're really looking forward to go to the real world in 2021. Well, we did get to field, but it was not quite as we planned it because COVID continued. So during that time, US Embassy made really clear that NASA team cannot go to Cape Verde. So quickly we established alternative plan. So we had a DC8 station in St. Croix, and then our European partners will be still in Cape Verde. But because of a COVID delay in Europe, they also have to push their time back to from original plan that was July, and they push all the way back to late September. And we started August. So that's one particular tragic event in the way that we sort of should stay together, we stayed in part. And I will talk about another unexpected event, which is our beloved program manager, Gil Jackson, passed away during our field campaign in St. Croix. It was a hiking accident. That ended up that we didn't end the field campaign in early September. Original plan is that NASA flight will take suitcase flight across Atlantic Basin over here. So we do the second half of CPEX to fly over this basin and still carry through that original planning, but we didn't get to do that. So we end up both separate and cutting half of the CPEX. So I will discuss a little bit more later on in these lessons learned of how field campaign works. And you always have to plan to these unexpected events. So then now I'm going to go through a little bit more details in terms of our CPEX field campaign. Basically, we had flights, and these flights end up sampled quite a diverse environment. That we have pre-tropical depression, Ida, and we were in there when Ida formed, and you all know how Ida made a huge damage in the US. But we did capture the first piece of Ida. And to my knowledge, this is the first time ever a well-instrumented field campaign captured a very, very early stage. And I have to be proud to say we beat NOAA to this because we saw a lot of things in that very, very early stage, even with a lot of NOAA's field campaign, and they were not able to capture very, very early stage of this. And then we also sampled quite a bit of saw, dust winds, ITZC convection, and also tropical TSK, and also dissipation, how they interact with the dry air, and a mature Hurricane Larry with dry air intrusion and ITZC saw. So it's very diverse and very interesting results. So now these are real flight tracks. So each one, I'm not going to go through the details except to say each flights we are really mindful about our Aeolus validation. So we basically fly all time that have Aeolus passes over in mind how we designed these field campaign flight tracks. And then we sampled a very diverse environment, the leading edge of dry air, middle of dry air, tropical cyclone formation stage, and then follows through that. And then we also had quite a bit of other sampling regimes. So this quickly just to see that we also have NOAA's Collaborator with a sail drone position over here, so we can fly right over them to use our aircraft data to look at a boundary layer and also the surface fluxes. And on the right side, which is our real instrument now with halos, and each time I have plotted these different vertical sticks are the drop zones. So if you see the, for instance, winds, downwinds, if you see the sticks actually have the same color, that means verification is good. So pretty much the drop zones and down measure pretty well. And also the lower panel is the halos measurements of relative humidities. I want to spend a little bit of time on this particular case, which we are set out to do, is looking at the interaction of the dry air with the ITZC, and we cross through to look at the cross section of the ITZC. So as you see this animation itself, and then how we fly. But one thing I do wanted to mention that on the aircraft, especially plane like DC8, you have a front seat to see the real thing outside the window. This is how visually top you look at the ITZC. It's very packed convection, but squeezed shallower than the deep convection over the warm pool. And also you have this upper level, the envelope decks, and they can actually penetrate pretty far outside. And we did have a wind measurements in this particular one, and also halo measurements. So basically you see the curtain plots through that with the aerosol concentration and the humidity, and lots of science results. I probably wouldn't have time to go through this, but just to show you how extremely dry conditions we're dealing with in this particular region when you have a dust, aerosol, and so on. And these often to be problematic for model to resolve these. So I'm going to give you one example of how these measurements can help model to really put everything together. As I said, the CPEX-AW have this unique capability to sample environment and convection at the same time with wind, that is dynamics, and aerosols and the clouds all together using aircraft. So the top panel is the wind curtain plot from our down instruments, also wind from drop zones, and the APR3 reflectivity is plotted in the grayscale here. So one important feature is that you can see this elevated boundary layer structure and very strong middle-level jet associated with extremely dry air and also a dusty air, right? So this red color is our dust concentration, and then the other color is humidity. So you can see the deep convection as I showed you in the picture, and this outflow in this region where you have this moisture punching through the dry air, and then extremely dry air maintain the middle level too. So we map out quite nicely. And I'll want you to pay attention to these wind structures. And we did use our real time in the model runs. We do forecast every day. So just make a comparison of high resolution model versus what we observed. And this is quite typical. Model we initialize with ECMWF forecast every day, and our high resolution model able to pick up where generally location where the convection is with some of the details missing. But the important thing is this wind jet is there, but not as extend as strong as observed, which is repeatable, this feature. And the wind in the boundary layer and the boundary layer structure is issue because it's a very shallow boundary layer, tend to be overly saturated. And this is not unique to this model. Almost all the model we looked have a similar problem. And this sort of looking through these lenses, we're doing this in real time. So it follows every day. Our team also very interested working in the tropical cyclone genesis for Ida. So we designed this particular flight with a lot of flight over our sail drones, and also we're launching sounds in both islands and so on, so on. So I probably don't have the details time to go through the details, except to say that we were flying this pattern, and this is during the time IDA was right close to formation. Hurricane Center forecasters was on the chat with us during the time we actually gave them the first center location and minimum sea level pressure reported in real time. That helped their forecast as well. One other example in this region, which is uniquely Atlantic, that's the drier intrusion in major storms. Some of the major storms never able to further intensify or achieve their potential is because these very dry air. And again, on the aircraft, you can see the dust when we fly through this region. It's extremely dusty, and you can see the convection really have a hard time to punch through these very stable layers and so on and so on. So again, these are difficulty for a model to capture, but the aircraft can really provide a piece of these environmental interaction with this high impact weather and stuff. So I'm gonna have to skip some of this. So we do have a data portal that hosted by JPL Svetla, and we have all our satellite data, all possible satellite you can think, that is all in this portal, and with a lot of global model forecast fields too. So if you can visit this particular place, you will find all the different satellite overlay, our flight tracks all available. It's available for all to use. So I'm going to go through a few things about our modeling team attempting to simulating these data in real time, and we're still working on this. So first example is Shuhua Chen's group in UC Davis, and this is the first flight when we fly through this very dry air, and this is halo, the surface, the wind from down and halo. So she is able to, using the GSI analysis field, and then simulating this data into the WRF dust model. And just quickly to say, this is observation at the top, and this is the background from the model that with her data simulation scheme, so she does analysis, she's able to gating these detailed dry airs and dust into the model, and then so you can see the difference between analysis backgrounds. And so is wind speed, data simulation, and certainly make quite a bit difference. Except I just have to say that the model is having hard time to simulating boundary layer data because the background covariance and also model fields is very stubborn. Boundary layer is one of the most difficult piece for any model to simulate it right, and not because the data is model biases problem. And so is wind. So during this time, we also have Hui Su's group in JPL. She is helping to examine the reanalysis product after the field, and really near real time and after fields. And just to see, can these data simulated product getting into a reanalysis field? So I just want to mention one thing, that the ERA5 is with the wind satellite data simulation, Aerosols seem to be way better than the GFS so far. That certainly have been compared in real time. This is one that Hui Su have done in terms of group and her associates. We're looking at ERA5 of this tropical storm, Ida, and this is a mirror to their both analysis field. The thing plotted is surface wind, and also the color is boundary layer heights. So as you can tell, the model, not only the wind is different, the boundary layer looks very different. And the difference between the two analysis field is actually quite large. So if you're using analysis field as a truth, I certainly encouraging you to think twice and to think a little more about what you're looking at. So in general, there's a lot of possibility to really understand what kind of things that observation get into model and get into analysis field. So you can talk to Hui about a lot more of her study on these details. And specifically vertical structures, ERA5 looks quite a bit different. This is the vertical structure of that particular tropical cyclone genesis. North-south cross-section, east-west cross-section, you can see the dry air in that environment. The mirror 2, which is quite different, mirror 2 seem to be always a bit shallower and not as high resolution. I suppose the resolution is slightly different, but boundary layer looks very different as well of the two. So the last piece of the data simulation is a high resolution model simulation by Jiaxia Pu from University of Utah. So she's taking the data of this particular one, focus on convection of this tropical cyclone genesis case. This is a mirror emerge precipitation and the control simulation, and it's really everywhere. This tend to be systematic for many high resolution models. They just send up convections, often having difficult time to organizing or sometimes overly organizing. But the data simulation, again, seem to help WRF to concentrate convection in some places. This is using our field campaign data. All of this work has been sort of like ongoing, and it's a very early stage of looking at the field campaign. So I guess I'm rushing through this just to quickly give you a few things, the highlights to summarize. And obviously you can ignore our data summary. This is something I put it here for our team to remind ourselves. So in the highlights, we have more than 120 researchers, including many graduate students, postdoc participated both remotely and also in St. Croix, Puerto Rico, and so on. So we have underflown quite a bit of Aeolus satellite overpass. We established quite a bit of a Calval part and fly that many, close to 6,000 kilometer data passes, even though we only did half of our field campaign. And our instrument operated really nicely, except to say that I'll talk a little bit about some lessons learned. Our drop sounds should be the most reliable instruments, and it turned out there's some mistake made right before the field campaign got started, and then the drop sound failed quite a bit unexpectedly. So then we also, I didn't have time to go through this. We have a sounding launching from both St. Croix and Puerto Rico, largely by University of Utah and the Oklahoma group with Puerto Rico students participated. So I'm gonna leave you with a few pictures just to sort of reflect the human side of a field campaign. Our partners in Cape Verde, and these are European teams that both the German Falcon and the French Falcon science team. And this is the Greek group. They were in the Cape Verde Islands for more than 2 months and collected a lot of data that will be ultimately put together and very useful. And also our team in St. Croix. So ultimately, this particular field campaign, Ed and I probably agree, this is probably one of the most difficult ones for both of us, even though Ed has most field campaign in our field, and I don't have as many, but at least this is my 11th one. I led more than half of that in the past, but this particular one that we lost our dear friends, our NASA program manager, Gil Jackson. The picture to the left is the one that is the last flight she took with us and 2 of my graduate students. We celebrated quite a bit during this field campaign. We have quite many women students and women scientists participated, probably most from any field campaigns I know in the past. And Gil passed away during the hiking trip. So we miss her a great deal. And then lastly, there's some pictures to leave you with this campaign that actually really hit several historical marks. One that I'm extremely proud of, Nikki, is our first woman flight director on DC8 since 1987. That's DC8 first flight. After so many decades, we finally have the first woman flight director on our flights. So I was chief scientist that day, and Ida is a graduate student for forecast lead, and also she was our drop zone operators. So during this field campaign, we have many people, we made a concerted effort to have our students being trained on our flights, and also during our time in St. Croix, balloon launchings, and our Puerto Rico students, look how much fun they had in Puerto Rico launching songs, and Ida, again, doing our drop songs, and we did a remote with many people virtual space, our forecast team, all our graduate students, and also scientists from the JPL and ADI with our graduate students. So I really appreciate everyone participating in the field campaign, especially this is a difficult one. During the campaign, we were all has to deal with COVID and also human tragedy during the field campaign. And many of our students grow up really fast during this field campaign, not only learning science, there's a lot of a human side of story that I would like to talk to you guys during our lessons learned next session. So I'll leave that, and thank you for your time, and I hope I gave you a little bit of information on our field campaign.